here. All right, section 5.4, the fundamental theorem of calculus. Okay, one of the most important theorems you're ever going to see. But you all actually saw some very important ones, and a very important one in section 5.3 as well. Okay, okay, let's talk about this. Let's talk about, we're going to get to what the fundamental theorem of calculus. I'll just show you what it is. This is the fundamental theorem of calculus. And it says that if you have a continuous function over an interval, then if you define a function g of x, as the integral from a to x of f of t dt, okay, and you might wonder, well, why is that integral a function of x? I'm going to show you why, okay? But if that's the case, then g prime of x is going to equal to the function f of x. Essentially, what the fundamental theorem of calculus is saying is that differentiation and anti-differentiation are inverse processes. That's really what the theorem says. And you know, you have your ebook, you can follow along here. But I want you to be comfortable about this g of x function. You know, g of x being equal to an integral. Oh, you know, what's that about? All right, so let's talk about that. In example 1, they talk about a function defined as an integral. Okay, and what they do is they define this g of x function as the integral from 0 to x of f of t dt. Now, if g is a function of x, then as x varies, g should change too, right? Unless it's a constant function, but that's not what we're going to have here. So one thing that might help you feel comfortable with the fact that we can define g of x as the, well, if we have the integral of f of t dt from limits x equals t equals 0 to t equals x, that's a function of x, g of x. So what they do is they say, all right, find some values of g, and then sketch a rough graph of g. So what they've done here in figure 2 is they've drawn this function f of t. They've drawn the function f of t, and first they want you to find g of 0. Well, g of 0 would just be the definite integral of f of t dt from 0 to 0. And that just equals 0. Because there's no area under the function if your top and bottom limits are the same. Okay, but then they talk about the area, they talk about g sub 1. And they're saying g sub 1 is the area of a triangle. Well, what they're doing there is, if you look in figure 2, if you look in figure 2 from 0 to 1 here, the area under the function f of t is a triangle. That triangle has base 1 and height 2. And the area of the triangle is 1/2 base times height, which gets you 1. Okay, are there any questions so far on what you're seeing here? All right. Well, then let's go here a little bit further in the problem. Okay, let's go to g of 2. Now in figure 3, in the second picture, well, first of all, g of 2 would be the integral from 0 to 2 of our function. And based on the picture, the second picture in this figure 3 here, second picture, from 0 to 2, well, you have the area of the triangle, which is 1, okay, from 0 to 1, but then you have the area from 1 to 2 is a rectangle. Base times height is 1 times 2, and that's how you get 3. Similarly, if you wanted to find g of 3, well, g of 3, they have the third picture in figure 2. But here you have to estimate that the area of the function, well, they're giving an estimate from 2 to 3. They're estimating the area of the function is about 1.3. So, I mean, if you were to go from 2 to 3 in that third picture, and you know, go with a height of 2, base times height, that'd be 1 times 2, which is 2. They're assuming that about let me see. They're assuming about 65% of that second rectangle is shaded, and that's how they're getting 1.3. So it's an approximation. Okay, and they keep going and going. You know, they're just trying to show you. They're trying to demonstrate straight to you in concrete terms what defining what this g of x function defined as this definite integral means. It is a function of x. As x changes, g of x changes, because you're adding more and more area. And don't forget, area added can be negative as well. So, like for instance, they do, like for g of 4, they have that in figure 3 in that fourth picture. They have some orange area which is negative from 3 to 4, and that's going to be approximately negative 1.3. And so g of 4 would simply be 4.3 minus 1.3, which is 3. Okay, so that's. Are there any questions on this so far? Maybe give me a thumbs up if you're reasonably comfortable. Betsua's good. All right, very good, Betsua. Okay, good. Shaka, Ian, John, and Sawyer, good. Thank you, everybody. And John's good too. All right. Well, let's go ahead. And I actually have, and Sebastian's good. Thank you. I have a few examples now that I want to. I mean, the book goes into then example. Well, and actually, I'll say here in Figure 4, just continuing in this example we just looked at, the g function varies with respect to x. You know, g of 0 was 0, g of 1 was 1, g of 2 was 3, g of 3 was 4.3, g of 4 was equal to 3.0. So once again, g of 0 equals 0, g of 1 equals 1, g of 2 equals 3, g of 3 equals 4.3, g of 4 is 3, and so forth. And what they do is they plot the g function here. They plot that g function. Well, they obviously plotted the 5, like they computed the g function for 5 values of x, and you know, so you get coordinates, so you can plot the g function, right? I mean, when x is 0, g of 0 is 0, and that's why this g function here, that's why that, I don't know if I can highlight that, that's why that starts at the origin. And then g of 1 was equal to 1. Okay, so that's why you got 1, 1 there on that red graph of g in Figure 4. You have 1, 1 as the next point. And then g of 2 is 3, so you got 2, 3. The graph of g passes through coordinates 2, 3, or the coordinate 2, 3, right? Or the point, I should say, the point 2, 3. So point 0, 0, point 1, 1, and point 2, 3, for example, are on the graph of G, and so G passes through those points. And G increases a little more, and then it decreases. And so they're just showing you graphically, hey, you know, G is a function of X. Okay, are there any questions on that before we move on? All right. All right, very good, Nicholas, very good. All right, so now continuing here, they get to some examples. They get to like example 2, and they have a few other examples. And I'd like to now go right to my notes for this. So let me go ahead and share. Let me see here, 5.4 here. And let's go ahead and do a few problems together. Okay, so let me give you a moment to copy this problem down. Okay, so here they've defined the g of x function as the definite integral from 1 to x of t squared dt. Now I'll make a comment here while I'm at it. When you have a variable as one of your limits, or it could be even in both limits, then the integrand here, the integrand, the function, okay, the integrand function can't be in terms of x. You have to use a different variable. So that's why they have t squared and then they have dt here. The variable you integrate with respect to cannot be the same as a variable in your limit, okay? Because it would be kind of not understandable, right? If that were the case. So okay, we're going to take the derivative. We're going to find g prime of x, and let me show you how to do this. So g of x is equal to the integral from 1 to x of t squared dt. So by the evaluation theorem, we're going to find the antiderivative of t squared, which we know is t cubed over 3. And we're going to evaluate that antiderivative at t equals x, that's the top limit, and t equals 1, that's the bottom limit, and take the difference. It's strictly an application of the evaluation theorem. The only difference is the top limit is a variable x instead of like a it's a variable, but it stands for a number. It's just that number can change. Okay, so I get then g of x. Hey, it is a function of x. G of x equals x cubed over 3 minus 1. Are there any questions up to here? Oh man, that is a good catch. I have an error here. Thank you, Ian. This should be, hold on, this should be a third here. Good catch. Good catch. Absolutely. Let me see here. Yep. Let me fix that in my notes as well. We'll do it right now. All right. One moment, class. Okay, thank you, Ian. So now g prime of x, and this should also be a third. G prime of x is the derivative of my function g. This was my function g of x. I mean, that's the definition of a derivative. G prime of x is the derivative of g with respect to x. This is just Leibniz notation here. Okay. And but we established that g of x was equal to x cubed over 3 minus 1/3. So I'm going to put in for g of x cubed over 3 minus 1/3. And if I differentiate that, I'm going to get x squared when I'm done. Okay, let me give you a moment to catch up here. Okay, so now this is very interesting, the result we got, because I mean, g prime of x, right? I mean, we know it's this, but g prime of x is equal to x squared. But remember that t squared, okay, let me just do a little bit lot going on here. Let me just, the t squared in our integral was f of t. Okay, that's what f of t is. And when I did the derivative of g with respect to x, I got x squared, which is f of x. So it looks like g prime of x is equal to f of x, where the function f is determined by the function under the integral sign. Isn't that kind of interesting? I mean, you're taking, yeah. Yeah, I agree. I agree, Sebastian. I agree, Rodrigo. I mean, you're taking the derivative of an integral and you get back the function, f of t. And that's no accident, class. That's no accident. Okay, that's no accident. So I want to show you why this is true. Okay. In other words, you know, why would this be the case? And I'll go to the next page to show you the proof if you're ready. Are there any questions so far? All right. All right. What I'm going to do is prove the fundamental theorem of calculus in a somewhat informal way. Okay. So what I did here, and I'm going to give you a moment to copy this, is I have two graphs here. Okay, I have two graphs. The first graph, I have this function f of t here, and the area here, the area, and I don't want to, like, this area here. What is that area? What is that area? Well, that area, since your limit goes from, well, the area under the function f of t from limits lower limit a to upper limit x would simply be this integral here. It would be that integral, the integral from a to x of f of t dt. But I'll call that g of x. So that's why I write that inside the area, just so you can see its area. All right, so let me give you a moment to copy that first picture down before I talk about the second picture. Okay, so now the second picture, what I've done is I've drawn the same function f of t, but I've drawn a little bit more of it. So it starts out at t equals a, but it ends at t equals x plus h. And so the area now here, the area under the function f of t, between f of t and the t-axis, that area would be the integral from a to x plus h of f of t dt. And I'm going to call that then g of x plus h. Okay, that's what the second picture is. Okay, same function. Okay, give you a moment to copy that down. Okay, now what I have here in the third picture is what I'm doing is I'm looking at the difference of these two integrals. Okay, the difference of these two definite integrals, these two areas. So if you take the area here of the second picture and subtract the shaded area in the first picture, that's going to get you this shaded area here. And that's just the difference of these two integrals. Okay, and you're going to see why I'm doing this. You're going to see why. You're going to see why I'm doing this. There's a reason. Well, I'm proving this. I'm proving this fundamental theorem of calculus for you. Okay, now in the picture, you notice, of course, this piece of area then would start at t equals x and end at t equals x plus h. And the width of that little interval would be h. And for this area, of course, the function f of t is the top part of the area. And what we want to do is we want to approximate that area, that purple area. Okay, take a moment to copy that. Yes, John. I will go back to the previous slide. Don't worry about that. Not a problem. So we have this purple area here. Okay, it's the whole area under the function f of t from t equals x to t equals x plus h. We represent that area by the difference of these two integrals, because it is the difference of those two integrals. Now, if we want to approximate that area, we could say, well, how can we approximate the area under a curve? Well, let's approximate it by looking at the area of a rectangle. So what I've done is I've drawn here a red rectangle, and the height of that rectangle is f of x, because I'm using the left endpoint, which is x. I'm using the left endpoint x to determine the height of the rectangle. The height is f of x, and the width is h. So the area underneath the curve f of t, which is this area, can be approximated by the area of that red rectangle, which is base times height, h times f of x. Now you'll note that the difference here of these two integrals is just g of x plus h minus g of x, right? Because those two integrals are functions of x plus h and x, respectively. Okay, and I'll finish up the proof here, and then John, I'll go back to the previous slide. Don't worry about that. But are there any questions so far? All right, may I go to the next page? All right, Yaki's good. Okay, John's good. So he's good. All right, Nicholas is good. All right. So what we have now is we have here g of x plus h minus g of x is approximately equal to h times f of x. Well, if I were to divide both sides of this approximation by h, I would have then g of x plus h minus g of x divided by h is approximately equal to f of x. Right? If I divided both sides, again, if I divided both sides by h of the approximation, I'm going to get this. And Ian's, and now, oh yeah, Ian, it's back. It's back. Definition of a derivative. We know that if we let h get smaller and smaller, the area of that rectangle is going to approximate the area underneath the function better and better. So the limit of g of x plus h minus g of x over h would eventually equal f of x, because as h gets very small, f of x times h is going to be almost equal to g of x plus h minus g of x. And therefore, g prime of x, because the left side of this, the left side here, is the definition of a derivative. G prime of x equals f of x. And this proves part one of the fundamental theorem of calculus. And I actually took that from the book and just put it there for your reference. Fundamental theorem of calculus part one, there's two parts. It's like a good movie, you know, good movies always have sequels, right? FTC1 is abbreviation for Fundamental Theorem of Calculus part one. Okay, let me give you a moment to copy that down. Make sure you're comfortable. Okay, and let me know, please let me know if you have any questions. Okay, please let me know if you have any questions. So this is really, I think it's actually, I mean, there's a more formal proof at the end of section 5.4 for the fundamental theorem of calculus. You know, this to me, I feel good about it. Okay, I feel good about it. So we just proven then that if g of x is the integral from a to x of f of t dt, okay, that function g is an antiderivative of our function f. In other words, g prime of x equals f of x. All right, are there any questions before we move on? All right, then let's move on here. So I want to show you this is called the Fundamental Theorem of Calculus Part 1, but let me just show you the entire Fundamental Theorem of Calculus. Okay, it is in your ebook. Let me bring it up here. One moment. Yeah, let me get it here. Oh, I'm sorry. Wait, John P. One moment. You wanted me to go back? on that slide for a moment. One moment here. So John, this is the slide you're talking about, right? Okay. Whoops. You're good. All right. All right. Very good. Very good. All right. On that note, I don't want to share the whiteboard. Hold on. I want to go here. Right. So the entire, hold on here. I got to find it. Yeah, the entire fundamental theorem of calculus, now you know what it is. Because the second part actually, the first part there, fundamental theorem of calculus, the first part we just proved. And the second part is the evaluation theorem that we proved on, that we saw the proof of that on Monday. So together, this forms the entire fundamental theorem of calculus. And from this, many good things happen. All right, so I just wanted you to see that, just so it's in your book. Comes right after example 5, but it basically shows that differentiation and integration, or anti-differentiation, differentiation and integration are inverse processes. Okay, are there any questions on that? Okay, all right, very good. Well, then let's get back to the examples we were looking at. Hold on here. Okay. All right, so in this problem, well, let me give you a moment to copy it down. Okay, so here's our function, g of x, and we want to find its derivative. Okay, well, by the fundamental theorem of calculus, part 1, g prime of x would be the square root of 1 plus x squared. So our f of t for that problem, our f of t was equal to the square root of 1 plus t squared. So g prime of x is equal to just the square root of 1 plus x squared. I probably actually should have had you, tell me what the answer is. I think you could have told me that. How many? Well, I think you could have told me that. I don't think I needed to give that to you. But are there any questions on it before we move on? Okay, Ian asks a good question. Yes, Ian, this works when your upper limit is x. You can apply the fundamental. So what Ian's asking is, in the problem here, the upper limit was x. But what if the upper limit were something different? What if it were something different? Well, we can deal with that too. As a matter of fact, that's going to be our next problem we're going to look at. Let's go to the next problem. Here we want to find the derivative with respect to x of the integral from 1 to x to the 4th power of secant t dt. So what you're used to seeing up here is an x to the 4th, right? Or an x, right? If it's an x, and by the way, the bottom, does it matter what the bottom number is? Like I have a 1 here, but if I had instead like a 7 or a 2 or a 3, does the bottom number matter at all? What it is? That constant limit on the bottom? Is that going to affect our answer? No, it is not going to affect our answer. Okay, so I guess for some reason well, no, it doesn't. I mean, the last one, the bottom limit was 0, right? So, well, how do you think we're going to do this problem? I mean, how are we going to do this? We don't have an x on the top, we have an x to the 4th. Let me give a little analogy here. Remember when you learned how to find the derivative? Now this is just an analogy, okay? The derivative of the sine of x, right? You learned that the derivative of, what's the derivative of the sine of x equal to? What's the rule tell you? The derivative of the sine of x is equal to the cosine of x. That's right. Okay. Well, suppose you had the derivative of something a little bit different. Suppose you had the derivative with respect to x of, say, the sine of x squared. Okay, let's say you wanted to take the derivative of the sine of x squared. What would you have to do? What rule would you have to use? That's right, Kelvin, the chain rule. So we still would use this rule here. It's just a chain rule would be involved. Well, we do the same thing here. We do the same thing here with this problem. Let me show you. So what I'm going to do is because I have an x to the 4th in the numerator, this integral, well, it's not a function of x because I would need I'm sorry. I have an x to the 4th as my top limit. If I had an x as my top limit for that integral, we would have, that integral would be g of x. But I have x to the 4th as my top limit, so I'm going to call the integral g of x to the 4th. I mean, that seems logical, right? And I want to take then the derivative of g of x to the fourth. Well, by the chain rule, that would just be g prime of x to the fourth times then the derivative of x to the fourth, which is 4x cubed. That's the chain rule. But then by the fundamental theorem of calculus, g prime of x to the fourth is just secant of x to the fourth. And so your final answer is 4x cubed times the secant of x to the fourth. Please let me know if you have any questions or if anything's unclear. I find this very helpful to put g of x to the fourth there underneath that integral, because I can relate it to what we learned. You know, that integral we normally write as g as a function of x, but that's when we have x up here. But when we have x to the fourth, I have g of x to the fourth, and then I'm taking the derivative of g of x to the fourth, so I'm just applying the chain rule. How many find that helpful to put that g of x to the fourth under the integral? Does that help you? I want to kind of doing a survey here. Okay, it helps you, Sebastian. Good, good. For me, it helps. Then I see, chain rule. Okay, but Sue likes it, John likes it, Chaco, excellent, excellent. That's good to hear, good to hear. All right, so I want to do one more problem here before I set you off to work. Okay, this is kind of the big enchilada, as they say. How many have heard that term? I don't know. My terms when I was your age, I don't know if you hear my expressions anymore. You know, this is like the big enchilada. Has anybody heard that expression, or is that like is that a millennial expression or not? Tubular. I'm not sure what that means, Nicholas, but the tubular problem I want to do here. All right. Well, here we go. This is what I want to do. I bet Sue has not heard of that. Okay. All right. All right. Wow. Look at this. I want to take the derivative of this function of x. Now we have a cosine of x function in the numerator, or it's the top limit. But then look, we have the bottom limit. Oh, that's not a constant. That's not a number. That's not an a. You know, that's a sine of x. Okay, so what are we going to have to do in order to apply the fundamental theorem of calculus, part 1, to this problem? What are we going to have to do here? Well, Sebastian, I see where you're coming from. And John knows that the chain rule is going to be involved. But there's something I want to do to this integral before I start taking the derivative with respect to x. That's right, Zoe. Very good. Split it. Very good. We want to split that integral. Okay, so let me show you how we're going to do that. Here's what we do. I'm going to express this integral as the sum of these two integrals using the property of integrals. And I split the integral up about the value 0. Now, incidentally, I could have used any number. I don't have to use 0. I could have used, you know, like 2. If I had the first integral like this, from the sine of x to 2, and the second integral goes from 2 to the cosine of x, that would have been okay. But I just split it along. I mean, this is just property of integrals. If you have the integral from a to c of f of x dx, got to make this look good, sorry. One moment. Okay, and actually this is a property of integrals. We learned about properties of integrals back in section 5.2. I'm not sure, well, you can split it. I'll tell you what, I got a better idea. Hold on. To make this intuitive, I got an idea. If you had the integral from 1 to 4 of a function, would it be okay to write that as the integral from 1 to 3 of f of x dx plus, I like to have space, class, I like to have space, I like things to be clear, plus the integral of 3 to 4 One moment, class. Does this here intuitively make sense to you? In the red box, I mean, there I just have numbers, you know. Does that intuitively make sense? Yeah, yeah. I mean, you're just taking the area under the curve from 1 to 4 and breaking it up into the area under the curve from 1 to 3 plus the area under the curve from 3 to 4. Well, it's similar to what I'm doing here. Similar kind of thing. And then the derivative of a sum is the sum of the derivatives. Okay. but I'm used to having, in the first integral here, I have a constant on top limit, and a function of x on the bottom. Well, I'm, if using the fundamental theorem of calculus, even with the chain rule, I'm used to having my function of x on top and my constant on the bottom. And so using the properties of integrals, if I want to switch the limits here, if I want to switch the limits in this first integral, I just then switch the limits but introduce a negative in front of the integral. How many remember that property? How many recall that property? Okay, hold on, somebody chatted here, but okay, Sebastian remembers. Good, good, good. Absolutely. And incidentally, a negative can be brought out in front of the integral sign, right? Or I'm taking the derivative of a negative function, but that negative can be brought out in front of the derivative. Wow, look at all the properties you're using here. Okay, and so now I get down to here. Let me know if you have any questions on that. And now it's just two chain rule problems. That gets me there. Please let me know if you have any questions. Okay, and then so this kind of work now is what I would expect to see on your final exam. For the final exam, remember all the problems. Well, the part one of the exam where you would show work, you have to show really good, complete work to get full credit. And I know sometimes students, what they do is, they'll, that of course, for old assignments after the due date's passed, you can go and look at the key, and that's good. You can look at the key, and if you had trouble with the problem, you can see the key will guide you as to the solution. But even the key leaves out steps. Okay, so you have to. So sometimes the key will leave out steps. Sometimes the authors just want to, the key is a guide, but it doesn't necessarily show all the important steps to a problem. And so you have to keep that in mind when you're doing work for your final exam, because I want you all to do well on the final exam, and I want you to get full credit for all the problems. Okay, so you have to always keep, just keep that in mind. And you can see here from the lectures, the work that I'm showing, the work that I'm doing, the work is necessary to help you understand the process. And I'm going to look for that same work when you show me that you understand the processes. Okay, so, all right, are there any questions before I move to the next page? I just want to write this answer here a little bit differently. All right, well, if you're good then, if there are no questions, okay, then I will go here. And then here is the final entire answer. It's really an incredibly cool problem. How many think this problem's really, I mean, you know, you got your chain rule, you got derivative of trig functions, you have fundamental theorem of calculus. You know, look at all the concepts used in this problem. I mean, how many think this is kind of a cool problem? Yeah, Nicholas likes it. Rodrigo likes it. Good, good. Well, let me stop the recording here.